your room, door closed, walls all around you, silent, quiet, seemingly impenetrable. On a light, and it politely stays in the room with you, bouncing off the walls, as if it understands boundaries. But your Wi-Fi, it couldn't care less. It slips right through those same walls, travels across rooms, and somehow connects you to the entire world. Now that's a little strange, isn't it? Because walls don't look like they have doors for invisible things, and pass through effortlessly, while others are completely stopped. So the question isn't just what is happening, it's why. Why does light, something we can see, get blocked, while Wi-Fi, something we can even notice, passes through like a ghost? To understand this, we have to start thinking a bit differently. Not in terms of things moving around, but in terms of waves, energy, and how matter responds to them. That way, the walls aren't really walls anymore. They're more like filters choosing what to let through and what to stop. And that's where the real story begins. And you're sitting in your room, door closed, walls all around you, solid, quiet, seemingly impenetrable. Light politely stays in the room with you, bouncing off the walls as if it understands boundaries. But your Wi-Fi, yet, couldn't care less. It slips right through those same walls, travels across rooms, and somehow connects you to the entire world. Now, that's a little strange, isn't it? Walls don't look like they have doors for invisible things. They seem continuous, dense, and completely sealed. If you throw a ball at the wall, it bounces back. If you shine a flashlight at it, the beam doesn't go through. It reflects or gets absorbed, or at best creates a faint glow on the other side if the wall is thin enough. Everyday experience, walls behave like barriers. They stop things that's them to do. And yet at the same time, your phone is quietly receiving signals that have passed through multiple walls, floors, and ceilings, carrying videos, messages, and voices, all threading their way through what looks like solid matter. A contradiction, like the wall is both a barrier and not a barrier at all, depending on what you are sending through it. So the question isn't just what is happening, it's why. Light, something we can see so clearly, yet blocked so easily, while Wi-Fi, something completely invisible to us, passes through with such ease. Is it because Wi-Fi is somehow stronger, behaves differently, or can be that the wall itself is not as solid and uniform as it appears? Making sense of this, we have to let go of the idea that light and Wi-Fi are fundamentally different kinds of things. In fact, they are much more similar than they first appear. Forms of electromagnetic waves, ripples of electric and magnetic fields moving through space. The difference between them is not their nature, but their scale. Light has a much shorter wavelength and higher frequency, while Wi-Fi has a much longer wavelength and lower frequency. That difference in scale turns out to matter a great deal, because when these waves encounter a material like a wall, they don't just hit it in a simple way. They interact with the tiny charged particles inside the material, in the electrons. And those interactions depend very sensitively on the wavelength of the wave and the structure of the material. Wow, which looks smooth and solid to us, is actually a complicated arrangement of atoms, empty space, and electrons bound in various ways. With its very short wavelength, the structure of the wall appears detailed and complex, strongly to the incoming light, absorbing and re-emitting energy, scattering it in different directions, or converting it into heat. The result, most of the light doesn't make it through. Wi-Fi signals, on the other hand, have much longer wavelengths, often on the order of centimeters. Compared to that scale, many of the fine details inside the wall become almost irrelevant. The wave doesn't see that it treats the tiny structures in the same way. Instead, it interacts more weakly, and a significant portion of its energy can pass through, though not without some loss. So what seems like a solid, impenetrable barrier at one scale becomes partially transparent at another. The wall hasn't changed, but the way the wave interacts with it has. From thinking about objects as solid blocks to thinking about them as systems that respond differently to different kinds of waves is the key to understanding what's really going. Stolia. We all here, if you want to get a better grip on what's going on, it helps to stop solid object and instead imagine it as a kind of complicated obstacle course for waves. Like a smooth barrier, but something more like a dense forest made of atoms, with electrons loosely or tightly bound, ready to respond when something disturbs them. The trigonometric wave arrives, whether it's visible light or a Wi-Fi signal. It doesn't just crash into the wall like a ball hitting a surface. It sends the electron inside the material into motion. These electrons begin to wiggle, oscillating back and forth under the influence of the incoming wave. And as they move, they themselves generate new electromagnetic waves, which can interfere with the original wave in all sorts of interesting ways. Now, here's where things start to separate. The way these electrons respond depends very strongly on the frequency of the incoming wave. For visible light, the frequency is extremely high. Its field changes direction incredibly fast, and the electrons try to keep up. In many materials, they respond quite strongly at these frequencies. Energy, re-emitted in different directions, or convert some of it into heat through internal vibrations. The result is that the original beam of light loses its ability to emit straight through the material. Sometimes the re-emitted waves cancel the forward motion of the light, effectively stopping it from penetrating deeper. It's sending it off in random directions. That's why most walls appear opaque. You don't see light passing cleanly through them because it's constantly being interrupted, redirected, and absorbed at a microscopic level. Wi-Fi signals, by contrast, operate at much lower frequencies. Their electric fields change more slowly, giving electrons a very different kind of push. In many common building materials, like drywall, wood, and even brick, the electrons don't respond as strongly to these lower frequencies. They still move, but not in a way that leads to strong absorption or scattering. Instead, the wave can induce a gentle oscillation that doesn't disrupt its overall progress too much. But energy is still lost. Walls do weaken Wi-Fi signals, but a significant portion continues onward, emerging on the other side with enough strength to be detected by your device. Another way to picture it is to think about the size of the wave compared to the gaps and structures inside the material. Visible light, with its tiny wavelength, is sensitive to very small features. It interacts with the fine structure of atoms and molecules, almost like trying to pass a very thin thread through a tightly woven fabric. It gets caught, tangled, and scattered. Wave, being much larger, are less sensitive to those tiny details. They behave more like a long rolling wave passing through a set of obstacles that are small compared to its size. The wave can effectively average out the small-scale structure, allowing it to continue moving forward rather than being stopped outright. This doesn't mean walls are completely transparent to Wi-Fi. Perfect signal everywhere. In reality, valve reduces the signal strength a bit, depending on its thickness and material. Concrete and metal, for example, interact much more strongly with these waves and can block them far more effectively. So instead of thinking in terms of can pass through versus can't pass through, it's more accurate to think in terms of how strongly a material interacts with different frequencies of electromagnetic waves, and how that interaction redistributes or absorbs the wave's energy as it tries to move through. There's another layer to this that makes the whole picture even more interesting. The materials themselves have preferences, not in a conscious sense, of course, but in the way their internal structure naturally responds to certain frequencies of electromagnetic waves more than others. Material is made up of atoms and molecules, and within those are electrons that can move, vibrate, or shift slightly when influenced by an external electric field. But these electrons are not free to do just anything. They are bound in specific ways, almost like masses attached to springs. And to a system with springs, they have natural frequencies at which they prefer to oscillate. When an incoming electromagnetic wave has a frequency close to one of these natural frequencies, the electrons respond very strongly, oscillating with larger amplitudes, absorbing more energy from the wave. Energy doesn't just disappear, it often gets converted into other forms, like heat, or is re-emitted in different directions. That's when the material becomes very effective at blocking or weakening that particular kind of wave. Visible light happens to fall right into the range where many common materials have strong responses. That plaster and things like paint, plaster, and wood are quite good at interacting with those frequencies. So when light hits a wire, not just a passive encounter, the material actively engages with the wave, taking in energy and redistributing it in ways that prevent the light from continuing straight through. On the other hand, usually operate in frequency ranges where these same materials don't have strong natural resonances. The electrons don't get excited in the same way. They still move a little, but the interaction is weaker, less efficient at absorbing energy. As a result, the wave is not significantly disrupted and continue propagating through the material with only partial loss. You can think of it like pushing someone on a swing. If you push at just the right rhythm, the natural frequency of the swing, the motion builds up quickly, and you transfer energy very effectively. Которая длится 100 лет or too quickly, the energy transfer is much less efficient. The swing still moves, but not nearly as much. In this analogy, visible light is like pushing at just the right rhythm, while Wi-Fi is like pushing a beat. There's also the question of how tightly electrons are bound within a material. For example, many electrons are relatively free to move throughout the structure. That's why metals are so good at blocking electromagnetic waves across a wide range of frequencies, including Wi-Fi. The incoming wave easily sets these free electrons into motion, and they quickly generate opposing fields that cancel the wave inside the material. Also, by placing a router inside a metal box, or even behind thick metal objects, can dramatically reduce signal strength. Которая material isn't just passively sitting there, it's actively responding in a way that prevents the wave from penetrating. Materials like air, plastic, or dry wood have electrons that are more tightly bound and less able to move freely. This limits how strongly they can interact with the thread. Or frequency waves like Wi-Fi. The wave can pass through it with relatively little resistance, especially over short distances. What we really see is a combination of factors. The frequency of the wave, the natural response of the materials, response of the materials, electrons, and how easily those electrons can move. All of these come together to determine whether a wave is mostly reflected, absorbed, scattered, or transmitted when it encounters something that at first glance just looks like a simple wall. Now, you cut this and step back a little. Something rather fascinating begins to emerge. That wall, solid wall, starts to lose its meaning. What feels solid to your hand, what stops a thrown object instantly, is not necessarily solid to everything else in the universe. Stability in this sense is not an absolute property. It depends on what is trying to pass through. Everyday objects like a wall or your hand. The wall is an effective barrier because the atoms in your hand and the atoms in the wall strongly repel each other when they get too close. Read by electromagnetic forces at a very small scale, and it gives rise to the sensation of hardness and impenetrability. But for electromagnetic waves, the situation is completely different. They are not trying to push through atoms in the same mechanical way. They are interacting with the electric charges inside the material. And that interaction can range from very strong to barely noticeable. A wall is not really a wall in a universal sense. It's more like a selective filter. It filters out certain wavelengths very effectively while allowing others to pass through with relative ease. That filtering is built into the microscopic structure of the material itself. This is not just a curious detail about Wi-Fi and light. It's part of a much broader principle that shows you why. Well, across physics, the universe is filled with different kinds of waves spanning a huge range of wavelengths and frequencies, from very long radio waves to extremely short gamma rays. Every chair you encounter interacts with the spectrum in its own unique way. That's why glass is transparent to visible light, but can block ultraviolet radiation. Certain plastics can let visible light through, but absorb. It's why you can use X-rays to see through the human body, but not through denser materials like bone to the same extent. Each case is just another example of how the interaction between waves and matter depends on matching or mismatching scales and frequencies. About Wi-Fi signals passing through walls, you're really just seeing one small slice of this larger pattern. The frequencies used for wireless communication were not chosen randomly. They fell into ranges where signals can travel through air efficiently and penetrate common building materials reasonably well, while still being controllable and safe for everyday use. Even then, the process is far from perfect. As the signal passes through walls, part of its energy is always being absorbed or scattered. You are from the router, and why certain materials, like thick concrete or metal, can create dead zones where the signal struggles to reach. And if you keep extending this line of thought, you start to realize that what we perceive with our senses is just a very narrow window into what's actually happening around us. Our eyes are tuned to a small band of frequencies we call visible light, and based on that, we form intuitions about transparency, about its solidity. That opinions don't necessarily apply outside that narrow range. So when something like Wi-Fi appears to break the rules passing through walls, it's not really breaking any rules at all. Feeling that the rules we're used to are based on a limited perspective, one that depends heavily on the particular kind of waves our eyes can detect and the way our everyday experiences have. That's to interpret